Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. In the grand tapestry of Indian scientific history, certain threads become entangled, their colors and textures so similar that later hands struggle to separate them. Such is the case of Aryabhata, a name that evokes the golden age of Gupta mathematics, yet which belongs to two distinct luminaries separated by 5 centuries. The first, flourishing in the 5th century, authored the seminal Aryabhata, a work that revolutionized Indian astronomy and mathematics. The second, the subject of our inquiry, lived and worked around the 10th century, composing a magnum opus of his own. This chronological and nominal coincidence has created a persistent shadow in the annals of science, a historiographical challenge where the monumental achievements of the latter figure are frequently absorbed into the legacy of his more famous namesake. Our purpose is to illuminate this shadow, to carefully disentangle these two intellectual legacies, and to grant Aryabhata II the distinct and profound consideration his work commands. This exploration is an act of historical recovery, an endeavor to reconstruct the world and the mind of a scholar whose contributions merit their own place in the pantheon of scientific thought. To comprehend the significance of Aryabhata II, one must first inhabit the intellectual landscape of 10th century India. This was an era of immense dynamism and consolidation. The great imperial structures of the past had given way to a complex mosaic of powerful regional kingdoms, each a center of cultural and scholarly patronage. This political fragmentation fostered a fertile ground for intellectual diversity. Within the domain of Jyotia, the traditional science of astronomy and astrology, this period was characterized by a profound sense of inheritance and the urgent need for synthesis. For centuries, Indian astronomers had operated within the frameworks of various siddhantas, or comprehensive astronomical treatises. These were complete systems of the world, providing the mathematical tools, planetary parameters, and cosmological models necessary to predict the movements of celestial bodies. By the 10th century, several major traditions held sway. The Aryabhata, the school originating from the work of Aryabhata, continued to be influential, celebrated for its elegance and mathematical ingenuity. Its primary competitor was the Brahmapakya, the system derived from Brahmagupta's formidable 7th century text, the Brahmasphurya Siddhanta. Brahmagupta's work was encyclopedic, critical, and deeply respected. He had famously critiqued his predecessor Aryabhata IV on several key points, establishing a powerful alternative tradition. A third stream of thought, the Saurapakas, are based on a version of the ancient Surya Siddhanta, also commanded a following, offering yet another set of parameters and computational methods. An astronomer of this period was therefore born into a world of competing orthodoxies. The central intellectual task was one of navigation and reconciliation. The foundational texts, while revered, were growing old. Centuries of observation had revealed subtle, yet undeniable, discrepancies between their predictions and the actual positions of the planets. This was the core problem of the age. The intricate celestial clockwork described by Brahmagupta and Aryabhata IV, while brilliant for their time, was beginning to show its age. The slow, inexorable procession of the equinoxes, the minute variations in planetary orbits, and the accumulation of tiny computational errors over generations meant that the tables and formulas of the past yielded results that an exacting observer could find wanting. An astronomer wishing to calculate an eclipse, determine the date of a religious festival, or cast an accurate horoscope faced a dilemma: which Siddhanta should one trust? How could one correct the established parameters without dismantling the entire elegant structure built upon them? The challenge was immense. It required a scholar with a masterful command of the mathematical heritage, a keen observational eye, and the intellectual audacity to forge a new, more accurate synthesis. It is precisely into this intellectual crucible that Aryabhata II steps, and his response was the creation of a work of breathtaking ambition, the Maha-Siddhanta, or the Great Siddhanta. The very title signals its purpose. This was conceived as a definitive, comprehensive and updated system intended to supersede its predecessors and become the new standard for astronomical practice. It was an attempt to absorb the accumulated wisdom of the centuries, to adjudicate the disputes between the rival schools, and to provide a single coherent and computationally sound framework for the whole of astronomy. The Maha-Siddhanta represents a conscious effort to resolve the intellectual tensions of the 10th century, to create a system that was both deeply rooted in tradition and responsive to the empirical needs of its time. It stands as a monument to the idea that science progresses through a continuous process of refinement, correction, and bold synthesis. Therefore, our investigation will proceed by dissecting this remarkable text. By examining its structure, its mathematical innovations, and its specific astronomical models, we can reconstruct the intellectual project of its author. We seek to understand the choices he made, the problems he prioritized, and the unique solutions he engineered. Through this careful analysis of the Maha-Siddhanta, a clear portrait of Aryabhata II will emerge, a figure of immense erudition and originality, a synthesizer and a reformer who sought to bring order to the heavens as they were understood in his time. His legacy is encoded within the 18 chapters of his masterwork, and it is there that we must look to secure his rightful and distinct identity. The architecture of this grand treatise, a deliberate and systematic argument for a particular vision of the cosmos, provides the necessary first step in this intellectual excavation. An examination of the Maha-Siddhanta's 18-chapter framework reveals the profound intentionality of its author. This is a text built with purpose, a cathedral of computation whose every element contributes to a unified whole. The scope of the work is encyclopedic, designed to function as a complete manual for the practicing astronomer-astrologer of the period. Its very organization serves as the first and most compelling piece of evidence for Aryabhata II's role as a systematizer. The treatise commences with foundational elements, dedicating its initial chapters to the bedrock concepts of Indian astronomy, the mean longitudes of the planets. This is the essential starting point, the establishment of an idealized average motion for each celestial body, a baseline against which all observable complexities would be measured. From these mean motions, the text logically progresses to the far more intricate problem of determining the true longitudes of the planets. This involves the application of sophisticated geometrical models and corrections, accounting for the eccentricities and epicycles that explain why planets appear to speed up, slow down, and even move backward against the backdrop of the stars. The chapters flow with a pedagogical clarity, guiding the reader from the general to the specific, from the simple average to the complex reality. Following this, Aryabhata II addresses the three fundamental problems of diurnal motion, or triprashna: direction, place, and time. This section provides the tools to connect the abstract celestial sphere to the observer's immediate terrestrial experience. The latter half of the Maha-Siddhanta transitions from planetary theory to its most dramatic and vital applications. There are detailed chapters on solar and lunar eclipses, phenomena of immense astronomical and cultural significance. The text provides algorithms for predicting their occurrence, duration, and magnitude. It continues with discussions of planetary conjunctions, the rising and setting of celestial bodies, and the phases of the moon. A significant chapter is devoted to spherical trigonometry, presenting the geometric principles necessary to solve problems on the celestial sphere. This comprehensive arc, from the definition of a mean planet to the prediction of a total solar eclipse, showcases an intellect committed to building a complete and self-contained system. The architecture of the work itself is an argument for a specific, ordered vision of the cosmos, one where every phenomenon could be understood through a coherent sequence of calculations. Within this grand structure, however, lies a foundational decision of immense consequence, a choice that defines the entire character of the Mahasiddhanta and distinguishes its author from his celebrated namesake. The central challenge for any astronomer creating such a comprehensive text was the reconciliation of competing astronomical traditions and parameters. A key point of divergence in Indian astronomy was the choice of epoch, the precise moment from which all celestial timekeeping begins. Two primary systems held sway: the Uddayika system, which reckoned the beginning of a civil day from sunrise, and the Ardharatrika system, which began the day at midnight. The first, Aryabhata, in his Aryabhata, championed the Uddayika, or sunrise system. This was the convention followed by many influential astronomers, including those who developed the widely used Surya Siddhanta. Aryabhata II, in a move of profound intellectual independence, elected to build his entire Mahasiddhanta upon the foundations of the Ardharatrika, or midnight system. This was a deliberate and system-wide commitment. Every calculation, every parameter, every temporal measurement in the text is oriented around a day that begins and ends in the deep quiet of midnight. The implications of this choice are far-reaching. On a practical level, it offered certain computational advantages. A day that begins at midnight allows for an entire night of observation to fall within a single date, a small convenience that a working astronomer might appreciate. One can almost picture the scholar finding a certain elegance in aligning the calendar day with the period of prime celestial visibility. The theoretical implications, however, are far more significant. By adopting the midnight system, Aryabhata II was explicitly aligning himself with a different school of thought, one that traced its lineage back to a lost work, also reputedly by the first Aryabhata, which supposedly used this very system. He was in effect claiming to be the true inheritor and reformer of this alternative tradition. This decision forced a complete recalculation and reformulation of astronomical parameters. Planetary positions, rates of motion, and epochal constants all had to be consistent with a midnight starting point. This created a work with remarkable internal consistency. The Mahasiddhanta became a self-contained universe of calculation, free from the potential contradictions that could arise from mixing parameters from sunrise and midnight systems. This choice reveals an author with a deep concern for logical purity and systematic integrity. He was crafting a coherent astronomical argument, presented as a complete and usable manual. His solution to the problem of conflicting traditions was to choose one and follow it with rigorous discipline. This act of selection and standardization elevates the Mahasiddhanta from a mere compilation of astronomical knowledge into a definitive statement. It represents its author's vision for how astronomy should be practiced, with consistency, with systematic rigor, and with a clear understanding of its own foundational principles. The text's very structure, a deliberate journey from first principles to complex applications, is built upon this singular defining choice of a midnight epoch. This framework of logical consistency provided the essential scaffolding upon which he could then erect his own specific mathematical and observational refinements. It is within this carefully constructed edifice that one finds his most brilliant technical innovations, such as the highly accurate method for generating trigonometric values, a tool essential for bringing his theoretical cosmos into precise numerical alignment with the observed heavens. The framework of logical consistency established within the Mahasiddhanta provided the essential scaffolding upon which Aryabhata II could erect his own specific mathematical and observational refinements. It is within this carefully constructed edifice that one finds his most brilliant technical innovations, such as the highly accurate method for generating trigonometric values, a tool essential for bringing his theoretical cosmos into precise numerical alignment with the observed heavens. This pursuit of numerical precision represented the very frontier of 10th century astronomy. The grand cosmic clockwork he envisioned, with its planets moving in their epicyclic paths against the backdrop of the stars, required a mathematical engine of commensurate power and subtlety. The predictions of eclipses, the calculation of planetary longitudes, and the timing of celestial conjunctions all depended ultimately on the quality of a single foundational tool, the table of sins. Existing tables, inherited from venerable predecessors like the first Aryabhata, were marvels of their own era. They had served Indian astronomy for centuries, enabling predictions of remarkable accuracy. Yet, the scientific impulse is one of perpetual refinement. For a mind like Aryabhata II, good enough was a starting point, a foundation upon which to build something better. The challenge was one of increments, of pushing the boundaries of precision ever further. Each additional decimal place of accuracy in a trigonometric value translated into a more reliable prediction, a closer correspondence between the world of mathematics and the world of physical observation. The problem, then, was how to generate a new set of values, a new sine table, that would surpass all predecessors in its fidelity to the true geometric form of the circle. This was a task demanding more than computational stamina. It required a profound insight into the very nature of the sine function itself. His solution is a masterclass in the power of iterative numerical methods. To appreciate its elegance, one must first understand the particular form of trigonometry practiced in classical India. The central concept was the jaya, or what we would call the chord sign. Imagine a circle with a very large radius, which we can call r. The jaya of an angle, theta, corresponds to the length of the half chord subtended by that angle. In modern terms, this value is equivalent to r multiplied by the sine of theta. Indian astronomers, with a characteristic flair for computational convenience, often chose a radius of 3,438 minutes of arc. This specific number arises because the circumference of a circle, calculated as 2 times pi times the radius, is approximately 21,600, which is precisely the number of minutes of arc in a full 360-degree circle. This clever choice of r forged a direct and harmonious link between angular measure and linear distance along the circle's circumference. With this framework in place, Aryabhata II articulated a beautifully concise and powerful algorithm for constructing his table. His method is what a modern mathematician would recognize as a second-order difference equation, a procedure that generates each new sine value based on the two that came before it. The process is recursive, building the entire table step by step from a minimal set of starting values. Let us trace the logic of this computational scheme. Suppose one has already calculated a sequence of sine values, which we can call ses sub n-1 and s sub n, corresponding to equally spaced angles. To find the next value in the sequence, ses sub n plus 1, Aryabhata II's rule can be expressed in 3 conceptual steps. First, one takes the most recently calculated sine, ses sub n. To this one adds the most recent difference, which is the quantity ses sub n minus ses sub n minus 1. This initial step essentially projects the next value forward as if the function were a straight line. Herein lies the true genius of the method. Aryabhata II understood that the sine function is a curve, and its rate of change is itself changing. A simple linear projection would accumulate errors. Therefore, he introduced a crucial correction term. The third step involves subtracting a small amount from the projected value. This correction term is calculated by taking the current sine value, s sub n, and dividing it by a specific constant, a constant derived from the square of the chosen radius. The full procedure, then, to find the next sine is this. Take the current sine, add the difference between the current and the previous sine, and from that sum, subtract the current sine divided by a fixed number. This single elegant rule, applied repeatedly, generates the entire table. The first term, s sub 1, corresponding to the smallest angular increment of the table, was typically approximated as the arc length itself, a valid assumption for very small angles. With this seed value, and the knowledge that the sine of 0 is 0, the entire intricate tapestry of 24 sine values could be woven, each one flowing algorithmically from its predecessors. The underlying mathematical insight is profound. The first difference, s sub n minus s sub n minus 1, is a discrete approximation of the first derivative of the sine function, which is the cosine. The rule essentially states that the second difference of the sine sequence is proportional to the sine value itself. In the language of calculus, this is a finite difference analog of the differential equation. The second derivative of y, with respect to x, equals negative k times y. This is the fundamental equation, describing simple harmonic motion, the very essence of periodic waves and oscillations, with the sine function as its canonical solution. Aryabhata II, working centuries before the formal invention of calculus, had devised a numerical method that implicitly captured this deep structural property of the sine function. This algorithmic power, the ability to generate a universe of precise values from a simple recursive rule, was a hallmark of his mathematical mind. The sine table he produced was a monument to this procedural elegance, a tool that empowered a new generation of astronomical calculation. This same intellectual posture, one that seeks to find unknown quantities through systematic step-by-step procedures, would find expression in completely different mathematical arenas. His work extended into the abstract world of indeterminate equations and the search for hidden numerical relationships, a field where the quarry was an unknown integer or an elusive irrational quantity rather than a trigonometric ratio. This algorithmic power, the ability to generate a universe of precise values from a simple recursive rule, was a hallmark of his mathematical mind. The sine table he produced was a monument to this procedural elegance, a tool that empowered a new generation of astronomical calculation. This same intellectual posture, one that seeks to find unknown quantities through systematic step-by-step procedures, would find expression in completely different mathematical arenas. His work extended into the abstract world of indeterminate equations and the search for hidden numerical relationships, a field where the quarry was an unknown integer or an elusive irrational quantity rather than a trigonometric ratio. The intellectual landscape of Indian astronomy was deeply concerned with cycles, with the grand repeating choreography of the cosmos. A fundamental problem arising from this worldview involved determining when celestial bodies, each with its own distinct period, would return to a state of conjunction. This was a question of cosmic synchrony, and its mathematical expression took the form of linear indeterminate equations. These are equations with multiple unknown variables for which a whole number solution is required. Consider an equation of the form a times x plus c equals b times y. Here, A and B might represent the number of days in the orbital periods of two planets, while X and Y would be the unknown integer number of revolutions. Each must complete to align in a particular way, adjusted by some constant c. Finding these integer solutions was essential for predicting eclipses, calculating the start of new ages or yugas, and reconciling different calendrical systems. Aryabhata II's great treatise, the Mahasiddhanta, provides a masterclass in solving these very problems. His primary tool was an ancient and powerful algorithm known by the wonderfully descriptive name Kutaka, which translates as the pulverizer. The method had been described by his predecessors, including Aryabhata II and the great Brahmagupta, yet his treatment of it stands out for its exceptional clarity and systematic rigor. The pulverizer, in essence, is an iterative process for finding integer solutions to linear Diophantine equations. It functions as a computational machine that ingests the large coefficients of an astronomical problem and, through a process of repeated division, breaks them down or pulverizes them into smaller, more manageable components. The procedure begins by using the Euclidean algorithm to find the greatest common divisor of the main coefficients. One coefficient is divided by the other, and the remainder is recorded. The divisor then becomes the new dividend, and the remainder becomes the new divisor. This process continues, creating a column of quotients until the remainder is zero. The existence of a solution to the original equation depends on whether this greatest common divisor also divides the constant term of the equation. Assuming a solution exists, the pulverizer then works in reverse. Starting from the bottom of the chain of calculations, it uses the recorded quotients to build back up, step by step, a pair of integers that satisfy the final simplified equation. Through a series of substitutions, this solution is progressively transformed until it yields the sought-after integer values for the original complex equation. Aryabhata II's exposition laid out these steps with such precision and lucidity that it became a definitive guide. He transformed a powerful but perhaps esoteric technique into a well-defined, almost mechanical procedure, a reliable engine for the astronomer's workshop. This was a profound contribution to Indian number theory, providing the essential algebraic machinery for the entire predictive science of the heavens. The intellectual elegance of this pulverizing algorithm found its counterpart in his treatment of another perennial mathematical challenge, the nature of irrational numbers. While the world of whole numbers and their ratios provided a comforting sense of order, reality frequently presented quantities that defied such simple description. The diagonal of a square with a side length of 1, the square root of 2, is a classic example of a number that can be approached yet never perfectly expressed as a fraction. For practical science and engineering, the philosophical conundrum of irrationality was secondary to the pressing need for highly accurate approximations. A geometer calculating land area or an astronomer modeling planetary distances required workable, precise values for the square roots of numbers that were themselves perfect squares. Aryabhata II addressed this problem with a method of stunning efficiency and insight. He presented a direct, iterative algorithm for finding the approximate square root of any non-square integer. His rule can be articulated as follows. To find the square root of a given number, one first identifies the largest perfect square less than that number. Let us call this perfect square a squared. The original number can then be expressed as a squared plus a certain remainder, which we can call r. The approximate square root of the original number is then given by the formula a plus the quantity r divided by 2 times a. Let us consider an example to appreciate the method's power. Suppose we wish to find the square root of 48. The largest perfect square less than 48 is 36, which is 6 squared. Here our value for A is 6. The remainder, R, is 48 minus 36, which is 12. Applying Aryabhata II's formula, we calculate the approximation as 6 plus the quantity 12 divided by the product of 2 and 6. This simplifies to 6 plus 12 divided by 12, or 6 plus 1, which yields 7. This initial approximation is useful, and the process can be refined. A more sophisticated application of the method reveals its true precision. For the square root of 10, the nearest perfect square is 9, so A is 3, and the remainder R is 1. The formula gives 3 plus the quantity 1 divided by 2 times 3, which is 3 and 1/6, or approximately 3.1667. The true value is close to 3.1623, demonstrating the remarkable accuracy of this simple two-step calculation. The true brilliance of this algorithm lies in its deep mathematical structure. This formula, giving the approximation as A plus R divided by 2A, is mathematically identical to the first two terms of the binomial expansion of the expression, the square root of the quantity A squared plus R. It is a linear approximation derived from what we would today recognize as a Taylor series expansion, a concept that would be formalized in European mathematics many centuries later. Aryabhata II, through a powerful numerical intuition, had developed a computational shortcut that implicitly captured the local behavior of the square root function. This method provided Indian mathematicians with a robust, reliable, and easily implemented technique for generating high-precision values for irrational roots, a critical capability for any advanced geometric or astronomical work. Together, the systematic exposition of the Kutaka and the elegant algorithm for root approximation reveal a mind obsessed with procedural perfection. Aryabhata II's genius was in creating and refining the very tools of calculation. He furnished the mathematical workshop of his era with instruments of greater precision and reliability. These algebraic and arithmetic techniques were the abstract engines of his science, the finely crafted keys he would use to unlock the secrets of celestial motion and recalibrate the cosmic clock. This part examines the application of Aryabhata II's mathematical skills to his primary goal, correcting the cosmos. The central problem for any Siddhanta author was the accumulation of observational errors in inherited astronomical parameters. Aryabhata II's solution was to systematically recalculate and refine these core values. We will detail his specific corrections to the mean motions of the planets and the length of the sidereal year, showing how he fine-tuned the existing epicyclic model. Furthermore, we will analyze his calculation of the Earth's circumference and compare it to values from his predecessors, highlighting the ongoing scientific effort to accurately measure the planet. His treatment of geographical longitude as a necessary correction for local observations will also be discussed, demonstrating the practical, applied nature of his work. With his intellectual armory thus assembled, Aryabhata II turned his attention from the abstract elegance of pure mathematics to the grand and pressing challenge that defined his life's work. The Mahasiddhanta was conceived as a monumental act of cosmic restoration. For a 10th-century astronomer, the universe inherited from the great masters of the past was a magnificent, intricate clockwork, yet one whose gears were slowly, almost imperceptibly, grinding out of alignment with the heavens themselves. The accumulated weight of tiny observational discrepancies, compounded over centuries, meant that the predictions of older texts were growing increasingly unreliable. The sun, the moon, and the planets, in their silent celestial procession, were ceasing to appear where the venerable tables said they should.
This divergence between calculation and reality was the central crisis of Siddhantic astronomy, and Aryabhata II's purpose was to confront it directly. His solution was a systematic, top-to-bottom recalculation of the fundamental parameters of the cosmos, a project of immense ambition and painstaking detail. The very heart of this endeavor lay in the correction of the mean motions of the celestial bodies. In the epicyclic model of Indian astronomy, a planet's apparent, often looping path across the sky is a combination of its average, uniform motion around the Earth, its mean motion, and the smaller circles, or epicycles, that account for its variable speed and retrograde phases. An error in the mean motion, the foundational speed, would throw off all subsequent calculations, creating a cumulative error that grew larger with every passing year. Aryabhata II, armed with his refined mathematical techniques and likely a wealth of contemporary observations, undertook the laborious task of re-deriving these values. His Mahasiddhanta presents a new set of figures for the number of revolutions each planet completes within the vast timescale of a Mahayuga. For instance, he posited that Mars completes 2,296,832,000 revolutions in this cosmic age. This profoundly large number, and others like it for Jupiter, Saturn, and the other planets, represented a subtle yet crucial adjustment to the engine of the cosmos, as he understood it. These were fresh constants, born of empirical diligence, designed to bring the theoretical model back into harmony with the observed positions of the planets, ensuring the long-term predictive power of his system. A paramount application of this corrective impulse was his redetermination of the length of the sidereal year, the time it takes for the Sun to return to the same position relative to the fixed stars. This value is, in essence, the mean motion of the Sun, and it forms the bedrock of any calendar and the entire chronological framework of astronomy. Aryabhata II's calculations yielded a sidereal year of approximately 365.25868 days. This figure stands as a powerful testament to the iterative nature of scientific progress within the Indian tradition. It represents a subtle refinement of the values proposed by his predecessors, a recalibration based on the evidence available to him. The act of recalculation itself, of daring to amend the work of giants like Brahmagupta, embodies the mature scientific ethos that progress depends upon meticulous verification and continuous improvement. His new value for the year was a declaration that knowledge was a living stream, requiring constant tending rather than a static monument to be revered without question. This project of cosmic measurement extended from the grand orbits of the planets down to the very globe upon which the observer stood. A pivotal achievement recorded in the Mahasiddhanta is Aryabhata II's calculation of the Earth's circumference. He arrived at a figure of 5,000 yojanas. To appreciate the significance of this number, one must first grapple with the historical ambiguity of the yojana itself, a unit of distance whose length varied considerably between texts and eras. Aryabhata II provides his own clear definition. One yojana is composed of 8,000 human heights, and a human height is 4 cubits. This internal standardization is a mark of his methodical mind. Using his specific larger yojana, his figure for the Earth's circumference converts to approximately 24,835 miles. This result is astonishingly accurate, falling within a mere fraction of a percent of the modern value measured at the equator. This achievement places him firmly within the global scientific enterprise, stretching back to Eratosthenes, of using celestial observation and geometry to measure our world. The method, while unstated, almost certainly involved measuring the difference in the Sun's noon altitude between two cities on the same line of longitude, a known distance apart, and then extrapolating that arc to the full 360 degrees of a circle. Furthermore, his work demonstrates a profound understanding of the practical necessities of applied astronomy. The celestial tables and planetary positions calculated in a Siddhanta were traditionally standardized to a prime meridian, often running through the ancient astronomical center of Ujjain. For an astronomer or an astrologer working in a different city, these tables would be systematically incorrect without a geographical adjustment. Aryabhata II explicitly addresses this with his detailed treatment of Deshantara, the correction for the difference in longitude. He provides clear rules for calculating this adjustment, which involves converting the east-west distance between the observer's location and the prime meridian into a correction in time. This correction would then be applied to the computed times of eclipses, planetary conjunctions, and other phenomena. This focus on geographical longitude reveals that the Mahasiddhanta was intended as a functional tool for practitioners across the Indian subcontinent. It bridges the gap between a universal, abstract model of the cosmos and the specific, local reality of an individual observer, making the heavens accessible and predictable from any given point on the terrestrial sphere he had so accurately measured. Through these interconnected refinements of planetary speeds, the length of the year, the size of the Earth, and the practicalities of local observation, Aryabhata II presented a renewed and revitalized vision of the cosmos, meticulously tuned and ready for the astronomers of his age. The intellectual rigor of this comprehensive overhaul was undeniable, yet the ultimate fate of this monumental work within the currents of scientific history would prove to be a complex and revealing story. The intellectual trajectory of such a comprehensive work, however, followed a path shaped by the prevailing currents of its time. The Mahasiddhanta, for all its mathematical elegance and corrective power, entered an astronomical landscape with established orthodoxies and powerful intellectual traditions. The monumental authority of Brahmagupta's Brahmasphuna Siddhanta continued to resonate through the centuries, serving as a foundational text for a vast network of astronomers. Later, the field would be illuminated by the brilliance of Bhaskara II, whose Siddhanta Uroma he achieved a synthesis of clarity and depth that would define Indian astronomy for generations to come. Positioned between these two titans, Aryabhata II's masterpiece faced a formidable challenge in gaining widespread adoption. Several factors contributed to its more specialized, and ultimately more limited, sphere of influence. The work's very sophistication, its dense mathematical arguments, and intricate corrective schema likely made it a demanding text for students and practitioners accustomed to other systems. An additional, and perhaps more decisive, element was its foundational choice of astronomical school. By anchoring his calculations to the Yordhara-Trika paradigm, the midnight reckoning inherited from the first Aryabhata, he consciously allied his work with a specific venerable lineage. This choice, while a testament to his intellectual allegiance, simultaneously set his treatise apart from the more widely practiced Brahmapaka school, the sunrise system championed by Brahmagupta, which had become the de facto standard in many centers of learning. His work became the crowning achievement of a particular tradition at the very moment that other traditions were consolidating their dominance. Consequently, the Mahasiddhanta was revered by a select group of connoisseurs, a text for the expert who could appreciate its subtle corrections and its fidelity to an older system, while the broader astronomical community continued to orbit around the more accessible and established canons. This relative quiet surrounding the Mahasiddhanta in the centuries that followed brings our inquiry full circle, returning us to the problem of identity with which we began. The very fact that a work of such intellectual heft could recede into the background of history, its author frequently conflated with his more ancient namesake, illuminates the profound importance of the distinction. The persistent confusion of the two Aryabhatas carries a significant intellectual cost. It risks effacing the specific, mature contributions of the second, absorbing his meticulous refinements into the generalized foundational brilliance of the first. To see them as one is to miss the narrative of development that their two careers, separated by 5 centuries, so perfectly encapsulate. The first Aryabhata was the wellspring, the revolutionary who established new parameters for Indian astronomy. The second was the critical inheritor, the master craftsman who tested, refined and strengthened the edifice he had been bequeathed. Acknowledging the second Aryabhata's unique identity allows us to appreciate the full spectrum of scientific activity, honoring the innovator and the synthesizer, the pioneer and the perfectionist. His historical faintness is a direct consequence of this confusion, a cautionary tale of how even genius can be obscured when the fine-grained texture of history is smoothed into a single, undifferentiated narrative. The career of Aryabhata II, when viewed with clarity, offers a profound meditation on the very nature of scientific progress. The grand paradigm-shattering discovery frequently captures the historical imagination, its narrative clean, heroic, and transformative. His work, however, represents an equally essential force, the patient, critical, and deeply intellectual labor of correction and consolidation. This is the activity of a mature science, one that has moved beyond its initial foundational axioms and has begun the difficult, iterative process of self-examination and refinement. It is the science of closing the gap between theory and observation, of accounting for tiny discrepancies that over centuries accumulate into significant errors. It is the demanding work of pushing a system to its absolute limits, polishing its every gear and recalibrating its every measure until it reflects the phenomenal world with the highest possible fidelity. His legacy, therefore, is an embodiment of this vital process. He demonstrates that intellectual courage is found in the willingness to challenge the calculations of revered predecessors. He shows that innovation can manifest as a more precise value for pi, a more accurate length for the sidereal year, or a more robust method for solving an indeterminate equation. These are the advances that ensure the long-term vitality of a scientific tradition, preventing its foundational insights from hardening into immutable dogma. Aryabhata II's contribution was to ensure that the astronomical science of his civilization remained a living, breathing discipline, capable of adapting, correcting, and improving itself from within. He stands as a powerful testament to the idea that the forward march of knowledge relies on the steady, rigorous, and often uncelebrated work of those who choose to build upon and perfect the great monuments of the past. His is the quiet triumph of precision, the enduring victory of refinement over stagnation, a crucial and illuminating chapter in the unending human quest to comprehend the cosmos.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.